Hello, everybody. Thank you so much for joining us. We are so excited to dive into Reflect, Refract, Engage. I am joined by two amazing presenters today, and they are going to introduce themselves in just a moment here. But as you and other educators are getting settled into the Zoom room, I do want to direct you to just one useful tool on Zoom. If you go to your Zoom window, so the window that you are watching this in, and you go to the bottom, you'll see what looks like a little chat bubble. That is going to be the Zoom chat. So that's where we're going to be taking questions. You can contact us there. We're going to be watching that chat like a hawk. And if we're trying to talk to you, we'll be reaching out to you there. If you click that chat bubble, on the right side of your Zoom screen, typically, or in its own window sometimes, you'll see what looks like a little chat box pop up. And that's where you can type your questions, comments, concerns in. At the bottom of that chat box, you'll see a little to section. And right now it might say to, and the blue button might say hosts and panelists. I'm going to ask that you go ahead and set that button to everyone. I ask that you send your questions to everyone for two reasons. First, and probably most importantly, it helps build community. So the more that we are sharing with other educators that we are still learning, that we're curious, that you're wondering something, other people in the room are probably wondering that same thing too. They want to make sure that it's okay for them to be curious. So it is helping us build that safe community for people to have questions, to be excited. And the second reason I ask that you send your questions to everyone is because we will be answering them live during today's presentation, and we don't want to look like we're talking to ourselves. So please make sure if you give us a question, set that to everyone so we can all share in that knowledge. To practice that skill, and I see you all letting me know where you're viewing from. That is awesome. Go ahead and let me know in that comment section. Let's see. Do you feel in your heart of hearts that Pluto is a planet? Let me know. And look, I know, but let me know what you think. Okay, let's see. Julia says yes. Laura Lee, who won our giveaway last on Tuesday, just a moment ago,
Oh,
says, "Oh no, where did Laura Lee go?" She says hello from Missouri. Let's see. Who else thinks? Okay, Lisa thinks Pluto is a planet. Glenda says planet. Jonathan says historically, yes, but hey, you know. Oh, that's so true, Trina. Trina shares Pluto is whatever it wants to consider itself to be. That's lovely. Oh, Blake says unfortunately no. Okay, we've got a Belinda says yes. Russ says no. Michael says yes. Will says no. Oh my gosh. Maybe I John says yes, the title got stolen. David says no dog in this fight. And you know what? That's fair. We are here to talk about waves and optics. And without further ado, let's get into some housekeeping items. So if we could go to the next page here. As always, you will get a recording of today's webinar. It usually takes us about 3 to 5 business days to get that edited and uploaded to our YouTube channel as well as our website. As soon as it's ready, though, we are going to email it to you. So keep an eye on your inbox. In that email, you will get a link to the recording as well as a link to the resources folder. I'm going to drop that link in the chat in just a moment here when I'm done talking. But in that resources folder, you're going to find a lot of good stuff from the team. So we've got today's presentation with clickable links. I dropped the certificate of attendance in there if you're using today's webinar for professional development. We've got experiments, all kinds of good stuff. So keep an eye in the chat for that link, and you're also going to get it to your inbox. As I mentioned before, we want to answer your questions during today's webinar, so please go ahead and make sure you drop those questions in the chat. Set that chat to everyone so we can all see what that question is. If we happen to not get to your question, or maybe you think of it later, or you start teaching a class and something comes up, reach out to us. We would love to help you out. Reach out to us at physics@vernier.com. There's a lot of other ways to reach out to us. I think that we have a slide at the way end of the presentation to talk about it. The last thing I'm going to say before I pass things off is stick around to the end. We are doing a giveaway of a Go Direct light and color sensor, which is really cool. We don't often give that away. So make sure you're staying with us until the end. I'm going to enter everyone's names into a random name generator, but you must be here to win. That being said, I have a poll to launch and I will let our presenters get to it. Thanks, everyone.
thanks, Dylan.
Thanks, Dylan.
One of the things that we want to be able to kind of tailor what we discuss here to the folks that are here. So we've got a few survey questions to help you or help us understand where you're coming from a little bit better. We find that a lot of folks that come to these webinars are already Vernier users, and that's great. We want to be able to help you learn to use these things, this equipment and probes in your classroom. And we know it's really an investment. It's not cheap, and so we want to make you help to get the most out of it. While you're filling that out, I guess a brief introduction for myself. Well, Fran and I are both members of the Science Solutions team here at Vernier. We recently changed the name of our group. Now we're Science Solutions team. Anyway, I'm what's called a teacher advocate. That means I help with if you have questions and you call or you text, or I guess if you chat really, or email. Fran and I were the people that would answer those questions. If you come to our trainings, whether online like this or an individual Zoom training or at like a conference, Fran and I were the people that do those particular trainings. We'd help with product development. So we'd represent the teachers in the product development process and give feedback and that sort of thing. And we do, we write lab activities and that sort of thing as well. Did I miss anything, Fran? I don't know.
I don't think so. We do all that and, probably more stuff, but it seems like it's almost a different thing every other day.
Yeah, it is kind of fun that way. I guess I'll add, both Fran and I were classroom teachers. We both were high school physics teachers. In fact, I can still remember when they reclassified Pluto as a dwarf planet, and there was this big discussion in my classroom around, why did they do that? What does that mean? Anyway, so I'm looking at the survey results. It looks like we got a lot of folks that already use Vernier products in their classroom. If you don't currently use Vernier products, we're going to kind of demo those things today. A lot of what we do, especially like the first lab, that's the thin lenses lab, you don't have to use our stuff to do it. It's likely that you could use the optics stuff that you already have in your drawer to do it. I'm always curious about where teachers do use lab work, how they use it, whether it's at the beginning of the unit to like introduce concepts or whether it's during the unit to kind of explore those. And I'm always interested to hear, especially like some instructors will do practicums at the end of a unit and use the lab activities kind of help students demonstrate their knowledge. And then it looks like most of you here are high school teachers. That's no surprise. I mean, Fran and I are both high school teachers. That's kind of where a lot of folks are find us. But if you're a middle school teacher or a AP college teacher, welcome, welcome. We have lots more stuff for you here. Today we're going to talk about 3 particular lab activities. One, the first 2 use our optics kit. The first activity is called Thin Lenses and Real Images. It's actually one of a pair of activities. I'll mention the other one that when we get closer to that. The second is called Light, Brightness, and Distance. It's about the kind of like students, measure the light intensity at different distances and see that inverse square law. Then we'll switch gears and we'll transport you out of this cave that I'm in right now. And Fran will turn on the lights and she'll show our emission spectrometer and kind of like the gas discharge tube. And the activity is called Spectrum of Atomic Hydrogen. We'll have time at the end for question and answers, but you're welcome to plug questions into the chat as we go along, and we'll do our best to answer those questions along the way. While I'm talking, Fran will be watching that chat, and if there's a particularly good or important question, she'll just interrupt me, and so we can answer it for everyone. And yeah, so let's get into this. Many of you probably have our Dynamics cart and track system, some version of it. We've made a couple over the years. All those cart and track versions come with a track, an aluminum track. Sometimes at first it was black, now it's silver. And that track you can use as an optics bench with this kit. All of these little pieces attached to the track, and there's a light source that has a couple of different images you can use. There's these are an aperture that you can funnel the light through. There are 3 lenses, 2 convex or converging lenses and 1 concave or diverging lens. There's a screen where you can catch the real images. And then these last little pieces here are this weird kind of bracket so that you can mount our light sensor to the track. We've made a couple of different light sensors over the years, and so it comes with these 2 pieces you only use the one for the light sensors that you have. So this expansion, so this optics kit is actually one of a few different optics kits that we sell. There's a mirror set that goes with these that kind of uses these same pieces, or you add on a color mixing set that, the light source is an RGB, LED sort of thing. There's a polarizer analyzer set that has 2 polarizing lenses that are, or I guess, polarizing filters that have angle measurements on them, so you can see what angle they're at relative to each other. And then there's also our diffraction apparatus, which includes, like a laser light source, a set of various, slit combinations, and then a high sensitivity light sensor to be able to detect the various light intensity as you move through the diffraction pattern that you create. I'm only going to use just this first one, the optics kit, this basic optics kit for two of the activities I'm going to highlight today. I'm going to go to this first one. This thin lenses and real images lab activity comes from our Beyond Mechanics lab book. This is a book it's a little more advanced. It's definitely geared more towards AP Physics or college level physics. It's generally kind of like a guided inquiry sort of thing where the expectation is that students already know how to use some of the software and probes and stuff like that. And so there's a lot more, there's less individual detailed instructions given and more specific kind of discussion questions, that sort of thing. This is really like, when I taught ray optics in my physics classes, this is kind of the lab that you would do in those. That's the first one of those. This one's thin lenses. It uses the 2 convex lenses that come in the optics kit. There's a follow-up activity called thin lenses and virtual images that uses the concave lens that comes in there. Because you're using the track, our dynamics track, that track has a ruler built into it. And you actually use the markings on that ruler in order to measure your object distance and your image distance. And this particular lab activity doesn't use our light sensor or anything like that. You're just catching the image on the screen that comes with the optics kit. But it does, you do want to, you create a data table and you plot or object distance and image distance. And so graphical analysis works great for that. I'm going to show you a little bit first how you collect data. And then one of the things that I put in the Google Drive folder was some actual sample data. And we'll pull that up and look at it together. I'll mention that at this point, in that Google Drive folder, you'll find a copy of this slide deck. You'll find, for each of these lab activities, you'll find a student handout and then also the teacher instructions. And then you'll also find a sample data. If it's for graphical analysis, like the 2 I'll talk about use graphical analysis, it's a file that ends with .gambl. Fran's going to use one. It's using a different app called spectral analysis. That one ends with an .smbl. I'm going to go out of here and go into graphical analysis. Okay, yeah. So here's that Google Drive folder. You'll see we're doing this first one, number 16, thin lenses and real images. I'm going to go to graphical analysis. This is the app here. I'm actually running it within the Chrome browser. You can kind of see that this is just another tab here in the Chrome browser. If you go to graphicalanalysis.app.app, it just loads the app within the Chrome browser. That's pretty handy because you don't have to get IT people to install it on your lab machines or anything like that. I'm going to do manual entry in this one. I'm just gonna plug the data in as I measure it off the ruler on the dynamics track. So I'm going to choose manual entry, and I know I'm going to measure two things. I'm going to measure the object distance and the image distance, and so I'm going to go here in my data table, and I'm going to change these X and Y labels. I'll change X to maybe I'll call this D. O for object distance, and I'm just going to measure that. It's going to be measured in centimeters because that's the markings on my ruler here. I'm going to change the Y column. I'm going to rename that to DI for image distance, also centimeters. That changes my axes here. And so the way this works is the students start off with the lens about 10 centimeters or 15 centimeters away from the 10 centimeter convex lens. So in this image here, or this video here, this kind of shoulder here that you can kind of see, that's actually, this right here is the light source. And then here is my convex lens. It has a focal length of 10 centimeters. And then here's the screen where I'm catching the image. The image itself is actually, it's a white light LED, and it's shining through an aperture that's in the shape of a 4 that's upright. Anyway, and I can actually, the way this works is the students move the lens so that it's some distance away from their, from the light source, and then move the screen to find the focal point. Where is that image being caught and created? And so like if I move this back and forth, like as I move too close here, you can see my image gets really blurry. And likewise, if I go too far the other way, it starts getting blurry again. That doesn't show as well for you as it does for me, of course. But if I come in right about here, I get to the point where it's sharpest, where it looks nice, clear. And so in graphical analysis, I would say, okay, I've got my light source at the 10 centimeter mark. I've got my image or my lens at the 25 centimeter mark. So my object distance, I would just plug in here 15. And the image distance, well, let's see, this guy is at 103. And this guy's at 25. So that's not quite 80 centimeters. That's going to be 83 centimeters. Oh, no, 82, sorry. So I'd plug that in here. And graphical analysis is going to drop a data point in the graph. If I move this another 5 centimeters, now my image or my object distance is 20. And I got to catch my image here. I'm going to move this guy a little bit. It looks like it's closer. There we go. That's looking better. Oh, no, too far. Right around there. So now my lens is at 30 centimeters and my image is at 63 and a half. So that would be 33.5. So I got 33.5. And I kind of go through this process. The lab has students, I think, do 5 or 6 data points. I could do that right now, but I took some sample data, so I'm going to do that first. So I'm going to go to my new experiment here. I'm not going to worry about saving this data, and I'm going to open this saved file. The file that I'm opening is I downloaded it from the Google Drive folder. It's this sample data, thin lenses and real images, sample data. I'm going to open that. And I did this for the two convex lenses that are in the optics kit. There's one with a 10 centimeter focal length and one with a 20 centimeter focal length. And you can kind of see the pattern here. It looks kind of like an inverse relationship. This is a little obscured. I'm going to change my axes here so a little bit to kind of make the relationship a little bit clearer. So I'm going to make the graph in the lower left corner isn't 0, 0. I want to make that 0, 0. So I'm going to make this I'm going to make that 0 there. And likewise, on the vertical axis, I'm going to make that 0 as well. So then I can see where 0, 0 is. And now it's not quite an inverse relationship. It's more like a hyperbola, you know, where the center of it isn't at 0, 0. You know, there's some asymptote one side along the vertical axis, and there's another asymptote along the horizontal axis. If I were to look at something like this and I wanted to figure out what that relationship is, my first instinct is to linearize this. And so what I'm going to do first is I'm going to say, well, if it's just 1 over, I would take and I would plot the image distance versus 1 over the object distance. So I'm going to do that in graphical analysis. That's fairly simple. I'm going to go to my data table, and where it says object distance in the data table, I'm going to click on the little 3-dot column options menu for that particular column of data, and I'm going to add a calculated column. And the name of this is just 1 over the object distance, and the units are going to be 1 over centimeters. And I can do this pretty easily. There are some canned expressions. I can do a custom expression. I'm just going to do this canned one, a over x, where a is just going to be 1 over my object distance. So I'm just going to do 1 over object distance. I'm going to apply that. It populated a new column here in my data table. I can see where it just did 1 over that. And now I want to plot image distance versus 1 over. So I'm going to go down here to the label axis label for the horizontal axis, and I'm going to choose 1 over the object distance. And well, I was hoping that would be linear. It's not, right? This is definitely not linear. Don't let anybody tell you think that this is linear, right? So then I say to myself, okay, let's try the same thing on the vertical axis. This also looks kind of like an inverse sort of thing. So I'm going to do the same thing. I'm going to go back to my data table, and I'm going to go to the image distance, and I'm going to do 1 over that. Okay, so click on the 3 dots, add calculate columns. 1 over image distance, also units of 1 over centimeters. I'm just going to do that a over x quantity, 1 divided by image distance, apply. And oh, that looks confusing. I'm going to get rid of that guy for now. I'm going to make this. That looks better. I only have one data set shown here. I want to see both of them to see if the pattern holds. So I'm going to go over here to, that's what was showing me the 10 centimeter double convex lens. I'm going to choose the same for the 20 centimeter one. And did it give me the same color? That was silly. I'm going to make that purple so it's a little easier to see. Okay, that looks pretty good. It's still a little wonky to me because the axes that it shows aren't what I want. I want this to be 0. I'm going to choose also to be 0. Why aren't you? Okay. There we go. All right, now I've got 0, 0. And I can see this actually does look kind of linear. So I'm going to do a curve fit on these. And I'll just go to my graph to options. This is, you can click and drag. You can also just, if you go to the graph options in the lower left corner, you can just apply a curve fit, a linear one. That's just what I want. I'll hit apply. And I can see that it's pretty good. You look at that R value and the root mean square. The R value is really close to -1. The root mean square error is pretty small. The slope of both of these lines is very close to 1. That's interesting, And then they both have a non-zero y-intercept. If you know the equation for lenses, thin lenses, 1 over DO plus 1 over DI equals 1 over the focal length, and you rearrange it in your brain, you're going to see that this intercept here is 1 over the focal length. So 1 over 10 should be about 1/10. That's this one here. That's pretty close, right? That's close to 1/10. And then 1 over 20 centimeters, that would be my other focal length, would be about 0.05, 5 hundredths. And this one is actually pretty close to 5 hundredths as well. The lab activity, if you look at it in the folder, it has, oh, here we are. It steps the students through this process of, I'll make this a little bit bigger. It steps us through the process of collecting this data. This is kind of what we've done here, and then evaluating that data. You'll see that they have, when you have a linear graph, choose a curve fit, and then use the best fit line. It has them go through this process and kind of derive this thing. The relationship general best fit line in terms of the object distance, the image distance, and the focal length. And then it goes into magnification. How does the size of the image compare to the size of the object itself? Anyways, this is a great lab. You'll find that most of our lab activities really they work all the time. The way we've gone through and refined the process so that you always get really good, clean data. The thing where they lack is that they're kind of dry. They're pretty bare bones in terms of like, here's a lab act, here's a procedure that works. The data comes out great. That really illustrates the principles that are being shown. And where it kind of misses out, I think, is on, how does this tie to real life? Sometimes there'll be extensions that discuss that. Sometimes in the introduction, I might mention a few things. For this particular lab activity, you might start off by talking about, correcting your vision if you wear glasses. What kind of lens goes into glasses for somebody that's nearsighted or farsighted, that sort of thing. That's great for these sorts of things. You might talk about magnifying glasses or telescopes. The lenses that were chosen for this optics kit were actually chosen so that you can make a telescope using the lenses in the kit plus your dynamics track, which is kind of fun. So that's kind of where you might have to bring in some of that real world. We're in the process of rewriting many of these activities that are more aligned to the more phenomenon-based kind of lab activities. We haven't gotten to this one yet, but this is kind of where you would probably end up going with that lab activity. All right, I'm going to switch gears a little bit. And I guess before I do, Fran, is there anything I'm missing or I should have mentioned while I was going through this particular activity?
No, I think this is all pretty good.
Okay. Let's talk briefly about this next one. This is this one you're looking for that inverse square law. You want to show that light intensity drops off as 1 over the distance. And it uses the same light source that we used in the previous activity. But rather than catching an image on a screen, we're going to use our light and color sensor to measure the light intensity. Our light and color sensor is this kind of box. It actually, it's a light and color sensor. So it has a sensor that just for visible light intensity. It also has an RGB sensor. So it reads red, green, and blue light separately. And it's kind of like a relative sort of thing, how much red light relative to green light relative to blue light. And then it also has an infrared sensor as well. It measures, I believe, both infrared A and B, if I remember right, or maybe it's mostly B. I forget. I'll have to look in the user manual though for sure.
It's actually ultraviolet.
Is it ultraviolet? Oh yeah, sorry, not infrared, ultraviolet. Wrong end of the spectrum here.
Yep. It was one of those. One of the ones you can't
Yes.
see.
And this particular lab just uses the light intensity sensor. And you mount it on this bracket that comes with the optics kit, and then you mount it at different distances away from your light source, and you just measure the intensity. This is also a little bit different. A lot of times in our physics activities, we measure things versus time. You're doing Newton's second law, and you want to measure velocity versus time, or you've got a force sensor, and you want to measure friction, and so you're measuring friction versus time, sort of thing. This particular lab activity uses a different kind of data collection. We would call it we call it events with entry, where the graphical analysis only collects data when you tell it to, and you tell it at different events. In the case of this one, the events are the distance, how far away it is from the sensor. And so we'll switch gears and we'll do that. I guess one thing that I'll note is the light source that comes with this optics kit. It has, it's an LED, and it over the first 15 minutes that it's turned on, it warms up a little bit. And as it warms, its brightness changes. And so this particular activity is one where we recommend that you let the light source warm up for about 15 minutes before you use it. So I'm going to move mine so you can see it a little bit better. Here's my light source. I'm going to right now, it's got this like 4. I'm going to change it so it's just a just bright light. I'm just blinding myself. And I'm going to put on my track. I'll put it at, say, the 40 centimeter mark. And then I'm going to move my light sensor so that it's 10 centimeters away to start off with. And in graphical analysis, I'm going to go back and I'm just going to do a new experiment. And I've got it. I'm going to turn on my sensor and I want to do sensor data collection. And I'm going to connect to this light and color sensor. I'm just connecting to it via Bluetooth, but you can also connect to it via USB. When you first connect to it, you have this option to choose, like, what do you want to measure? And there's light, UVB, and then the 3 RGB channels that you can choose from. I'm just, like I said, this is just the light sensor. I'm going to go, and right now it's set up to, for my graph, you can kind of see it's set up to record illuminance versus time. I want it versus distance, and so I'm going to change from time-based here in the data collection settings to event-based. And I'm going to choose events with entry, and this event is going to be distance, and I'm going to measure it in centimeters. Again, I'm just going to read the distance off of the ruler that's on the dynamics track. You can see when I do that, now my data collection window looks a little bit different. And I have a collect button, but then you can see there's also this keep button that's kind of grayed out. And I've got a data table here where it's got distance and illuminance. I'm going to first kind of zero things out as best I can. So I'm going to go and I'm going to move. Maybe I'll go this way and see if I can block all the light coming from my light sensor. Maybe I can go a little bit farther. There we go. And you can see it's still reading 1 lux, but I'm going to call that 0 for the sake of my lab right now. And I'm going to go back to my light source, and I'm going to hit collect. And now I'm ready to collect data. I'm at 10 centimeters away. I want it to collect the light intensity that it's reading right now. So I'm going to choose keep. And it wants me to add, it prompts me to say, well, what distance is this? What event are we doing here? And I'm going to say 10 centimeters. And I'm going to hit keep point. And now I can change things however I want. It's not going to collect any more data until I hit keep again. So I'm going to just move it a centimeter away, farther away. So it's at 11 centimeters instead of 10. And I'm going to hit keep. And I'm going to put 11 in here. And I'll keep that. And now I have 2 data points on my graph. I'll move it another centimeter. And hit keep. And that's 12. I can kind of see that looks like a line right now. Let's move it another centimeter and see if that trend continues. Okay, hit keep. And now I'm at 13. And it's looking a little bit. I can continue this. And that's kind of how I put some more sample data in here just because this takes a little bit of time. I'm going to show that sample data. Don't need to save that. I'm going to again choose my sample data, this light, brightness, and distance sample data. And I'll open that. And you can see I did the lab has the students do 10 to 20 centimeters away. Just move 1 centimeter at a time. And then once you're 10 centimeters away, then it kind of jumps out and it goes to 30 centimeter or 20 to 30 to 40 to 50 to 60 and so on. And you can see that what looked like started off looking linear, definitely that trend doesn't continue. So you could linearize this again. You could say, okay, this might be, you want to plot 1 over the distance or something like that. You can also, from the curve fitting options, one of the options is rather than linear, you can choose an inverse squared relationship. And if you do, you can see it matches it pretty well. It gives you an estimate for that fitting parameter A, and then it also gives you a root mean square error. Right now it's on the order of about 70, which is pretty small considering that the illuminance that I'm measuring ranges from about 3,000 or 3,200 there all the way to about 119. So a root mean square error that of a total of 70 is actually pretty good for that data. This particular lab activity, it's pretty simple, right? You're just collecting illumination versus distance. This is a good example of an inverse square law. They show up in lots of places. If you wanted to connect this to something that students know about, you might connect this to things like cosmology, especially if you talk about modern physics and you want to talk about the expansion of the universe. It's great to talk about light intensity and how that changes with distance, because we often talk about use light as our cosmic ruler. Do we want to measure? If we want to know how far away something is and all the information we get from it is the light that's coming, we might use that intensity to figure out how far away it is. Another application that's kind of interesting, especially it's also very different, is if you get radiation therapy. You have cancer and you have radiation therapy. They're shooting X-rays at you, and the intensity of that X-ray varies with the distance. And how much it does is this inverse square law. And so the dosing, how much radiation particular parts of your body gets, depends on that distance. And so that's kind of an important measure. That's something that like a medical physicist that that runs the radiotherapy sessions, they would take that into consideration. Is how far away is the tissue that they want to irradiate, and then how far they need to move everything in relation so the correct dose is applied. Trying to think. Anything I've forgotten, Fran?
There was, I don't think you've forgotten anything. There was a little bit of discussion about looking at how exoplanets are detected and will this light sensor work for that. So yeah, that was kind of neat to talk about. And we also talked about the units, because the older version of the light sensor was a relative sensor, and this one actually does measure luminance and lux, as you pointed out. So
yeah, there are older versions. Those older versions, I think they still work just fine for the inverse square law. It's just that the units were a little, kind of had to wave hands a little bit for those guys. Okay, Fran, I'm going to stop sharing here. Do you we'll switch gears and we can talk about, rather than capturing light, we're going to emit light?
Actually, before you stop sharing, could you actually just go ahead and show the next slide, and then you can stop sharing after we've talked about it.
Okay.
All right, here we go. So I get to talk about the fun stuff, which is technically chemistry, but it's also physics. And I'm not a chemist, but I did take quantum. So talking about emission spectra and how light actually is created. It's coming from these transitions of energy, generally electrons, from a higher energy level to a lower energy level. And when they make that transition, since they're essentially losing the energy, or their system of the atom is losing energy, that energy has to go someplace, and it's emitted as a photon. If we want to talk about, quantized light, or you can talk about if a bunch of them are going, it has definitely wave behaviors. So the classic, of course, is the simplest atom, the hydrogen atom. So that's what we're going to look at, because that's really a physics thing, not a chemistry thing. In physics, we want to look at the very simplest possible thing, not anything complicated, which is one of the reasons I like physics. So we're looking at the Balmer series, and there's five nice lines you can see here. We've got a red one, which is the hydrogen alpha line. We've got a sort of a turquoise one, and then there's a blue one and two violet ones. So we're going to be looking for that. If you're going to be doing in your classes, and like Josh pointed out, our experiments written in our books, and you do have this one. It's the hydrogen spectrum lab. They are kind of dry, but so there's some phenomena here. You could talk about neon lights. Those are increasingly rare these days, as many have turned to LEDs. But their neon lights are directly, you're exciting atoms with electricity, and then as they unexcite and then re-excite, you're getting these photons that are getting sent out. The composition of distant stars. So Josh was just talking about distant stars in terms of what the intensity, or how much light we can see from them, and that inverse square law and figuring out distance. Well, we can also use the light coming from them to learn about the composition of them. Are they a young star that's full of hydrogen? Are they an older star with a lot of helium and hardly any hydrogen left? Are they, beyond that and starting to actively turn that helium into additional elements? So cool stuff that you can talk about that. And also the auroras, which, it feels like in the past couple of years, there have been a fair number of big solar flares and storms where they've been, oh, you could see this aurora as far south as, Las Vegas, or you could see it as far as North Carolina or something like that. And so that's been pretty exciting. And I don't know how many of your students have actually seen those, but what is it with the auroras? Well, for most of the light you're seeing, that's coming from the nitrogen and the oxygen in the air, where the high energy particles are giving those electrons in the nitrogen and the oxygen some energy, and then they're coming back down to a lower level and mostly giving off a green glow. And so those different colors of light, different amounts of energy. And so we're going to use the spectral analysis app, and I'm also going to use an optical fiber. And Josh, now you can go ahead and stop sharing your screen, and I'll go ahead and take over. Great. So first, the fun part is I'm going to try and get my Zoom here to actually look through my camera of my phone. Yes, it did it. Okay. So I'm using, this is our single tube spectrum tube power supply. And this is labeled hydrogen. They don't come with the label. But this is our little, this is the glass tube that has the hydrogen gas in it. And it comes in this nice plastic thing that is very safe. It's difficult to break the glass, and it's only going to go in this thing one way. If you turn it around and do it the other way, it actually literally does not fit. So it goes in there. I'm also using our go direct emission spectrometer, and I've connected an optical fiber. You do not need the optical fiber, but if you don't use it, you have to kind of manually aim this at your light. So it's easier to use it for spectra. So if I turn it on, I get my lovely, bright pink looking hydrogen glow. So I'm a big fan of hydrogen. It's pretty darn cool. So let me then switch to sharing my screen. See. Do I want to share? Nope, that's the wrong thing. Don't look at that. I'm trying to share this. Let me see if I can get that back. Not that. This is always exciting. Well, I'll just share this. And now I will, can you see spectral analysis?
Yep.
Awesome, I'm sharing the right thing. All right, so I've got spectral analysis connected up, and I need to connect my spectrophotometer. And notice this is, I'm in the Chrome browser, and I've gone to spectralanalysis.app. That's the right thing to do here, and I need to connect a spectrometer, and I want to do this using USB. I don't have a USB cable for this. I'll be right back. It's on my desk.
Well, Fran grabs that. I guess one thing that I'll mention about the spectrometers is this particular spectrometer is our emission spectrometer. It's designed for these gas discharge tubes and that sort of thing. We also make another device called the Go Direct SpectraVis Plus.
I'm back. Were there any good jokes that I missed?
No, I was just explaining that we make another spectrometer called the Go Direct SpectraVis Plus that is primarily a chemistry sensor, and you can use it to do emissions, experiments. But this is really the better one for it.
Yeah, and funny thing, this one, it still thinks it's a SpectraVis when it's pairing, but it's the emission spec, and that's the label on it. So now I've connected it, and I want to do emissions, and I'm doing wavelength, full spectrum, and I get this lovely screen. I'm going to make it a little bit more visible. All right, and I like that it has the spectrum on the bottom here, so you can kind of see, all right, this is what colors that we're going to be seeing. And in order to collect my data, I'm just going to start collect. And this is what you see. So I'm going to stop collecting, and you can see there's a point here, and that's at 1. This is a relative intensity, like that old school light sensor we were talking about. And this is at, let's see, 656.6 nanometers. That's correct. This is definitely hydrogen. We've got another one here at 486. That's our turquoise one. And we've got one of our violet ones here at 433.7. But while that down here might be, I don't want to really do that. It might be that that's the other purple one, but I don't really know for sure. It's kind of hard to tell. It's a little bit different from what the it could just be noise. So in order to confirm that it's not noise, I'm going to actually have to supersaturate the collector. Now, what is the collector? It's actually a CCD, which is a charge coupled device. This is your standard early digital camera sensor. And I don't know if you noticed when Josh was doing his stuff, when he was had the camera showing the light source for the intensity versus distance, and that light in the camera view was really bright. It did not, it looked like kind of like a ball of light instead of a point source. Well, it truly is a point source, but the camera, unlike the human eye, has trouble when there's a very large difference between the amounts of light, when there's really dark and there's really bright. And so since most of the room is dark, that little point LED saturated the camera's view. And so what we're going to do is we're going to make the spectrometer saturate, and we're going to do that by increasing the integration time. So I'm going to change this from 30 milliseconds to 100. I'm going to make it 100 milliseconds. And what that does is it says, all right, instead of just taking a real quick look, we're going to take a slightly longer look. We're going to look at this for a whole tenth of a second. So I'm going to go ahead and collect that data again. And now I have a new set. And you can see that here it is. This looks pretty much exactly the same, but this new graph up here, it's a little bit wider up here. That's your saturated part. It's making that really bright line look wider, bigger than it would normally. This one's really showing up. This one's really showing up. This one down here is still of a maybe for me. It doesn't want to, that one, still of a maybe for me. And so I'm actually going to go ahead and ramp this up all the way to almost a third of a second, and say, all right, let's really get this. So I'm gonna hit collect, I'm gonna hit stop, and yes, now I can definitely see that purple line down there, and that purple line is at 410.6 nanometers, and I definitely expected a 410 nanometer line there, so I'm really happy with this. But if we were to look at just this part, you can see, well, even that first measurement I took was oversaturated, and you can see that by the flat top here. And the wider that line is, so maybe, I don't know, was it the point here at 655.9, or was it a little bit over at 656.6? How would I suss that out? Well, I'm going to do the opposite thing. I'm going to take this and I'm going to drop that down to maybe, 10 milliseconds. Oh, I can't go all the way down to 10. The lowest I can go is 15 milliseconds. And when I collect data at 15 milliseconds and look at this part again, now I have a point, and that point, that highest point, is at that 656.6 nanometers. So the trick there is just changing how long a time the emission spec is looking, and that's going to change whether or not it saturates and starts looking like a bigger picture. Josh, am I missing any questions here?
Nope.
Cool, because I went through all that really fast.
I guess one thing that we didn't mention that maybe we should have. I know many folks have used Logger Pro in the past, and you can use Logger Pro to collect sensor data, to manually enter and analyze data. And then Logger Pro also had you could connect a spectrometer like the emission spectrometer and collect spectra that way. Nowadays, we've Logger Pro is slowly aging, and we are in the process of replacing it with a few other apps. So graphical analysis is the big one. That's one I used earlier today. Spectral analysis was created just because this data collection method of collecting spectra and with these integration times and that sort of thing, it's just so different than the normal sensor data collection. It was really worthy of its own app. Likewise, the video analysis features that were in Logger Pro have also been spun off into their own app. That's called video analysis. We've done a few webinars about video analysis and that sort of thing. But just so if you're used to Logger Pro, these are the same tools. They're just kind of been separated out into their own apps.
Yep. I think we're ready for the any additional questions part. So that's cool. This is again kind of a chemistry thing that Jonathan has suggested, which is doing some red and blue food coloring in water and doing the absorption spectrum both individually and then together as a combination, which is really cool. And then, Daniel is talking about showing the lines, measuring them, and then calculating the energy differences between the levels and can connect each line to its corresponding transition. Exactly. Yes,
Very
it's
cool.
awesome.
Yeah, very cool.
All right, and then Carlos, I'm glad that you've been enjoying the app. I'm glad that you're getting good results with it.
All right. Well, I think we've got some time right here at the end for a drawing, Dylan.
Yeah, so as Fran and Josh were talking, I entered everyone's names into a random name generator to select the winner of a Go Direct light and color sensor. And the winner is, and I hope I'm pronouncing this right, Aurelia K. Aurelia. So congratulations. I'm going to email you right now to get some shipping information from you. Shoot me an email back when you see it. Check your spam if you don't see it in the next 5, 10 minutes. But huge congratulations. We don't often give away that sensor, so super exciting.
All right. Thank you, everyone. We will,
Yes.
like
Thank you, everyone.
Dylan mentioned, this will be posted in about a week or so to our YouTube. You'll get an email with a link. Thanks again.
Yep. Thanks all. Bye now.
Bye.